Good afternoon, good evening. There's a few people here. Today I'm going to introduce, the topic has already been introduced. You learned about scatterplots and visualizing two variables at a time in Unit 2. So I'm going to pick up from there. I'll just wait for people to come in because I didn't give you any warning. I don't have to give you a warning. You should know I'm going to live stream, but I can understand if you haven't heard from me. You probably wonder if it's going to even air. So how's everybody doing? Good evening. In terms of the videos on this topic, I'm gonna just remind you, you do have the videos that are listed in Moodle. So I guess the videos are video 17. Video 18. Video 19, and then I do some review stuff. 18. Also, after I finish with Unit 2, I begin Unit 3 and I have a few videos. Let me see, I'm sorry, V19. Okay. So you should have watched these already. Let me know if you have not watched these. And there's just a few videos. Video 48. And 49. And 50. So these are the introduction, and then this is Unit 3. There's other videos that just review exercises. And then, of course, these are in the StatsLongobardi playlist. It's kind of messy, isn't it? Okay. All right, I'm just waiting for people to come in. So how many of you watched all these videos? So let's say, how many of you at least saw these? Or no, didn't see these? Who did not see these ones? You should have seen those already. No one wants to admit. It's going to depend on if I talk about this again. So in this discussion, so my question is, who has not watched these videos in Unit 2, where I introduced the idea of two variables and observing relationships between two variables. Because until this point, you'd only looked at and analyzing and summarizing one variable at a time. Maybe you looked at one variable in different groups, like in the hot dog example, but it's always one variable. But then I introduced the idea of scatterplots, which is two variable analysis. And just like with one variable analysis, you begin with a graph, a graphical depiction of the data that's been collected. The two variables usually can be, I don't say usually, but often are distinguished between response and explanatory variable. And what we're trying to say there when we do that is that the independent or the explanatory variables influence the response. So the explanatory variable or the independent variable, that's another name for it, gets the label X on a two-dimensional axis. We would name that X on the horizontal, and then in the vertical we have the response variable plotted. Because it depends on the explanatory variable, it's called the dependent variable, and we use the letter Y, which is a standard for the vertical axis. So what are we doing? What we're trying to do when we look at two variables is we look for a relationship between them. Okay, why would we observe two variables unless we were trying to do that? I don't know. So we're trying to observe if there's a relationship between them. Now, whether one causes the other is a separate question. All right, we use this terminology, and you need to decide which of the two variables or what relationship before you start. What your relationship. Oh, I can't do this. I gotta put my iPad flat. You need to decide which one you're going to put on the X and which one you're going to put on the Y. I introduced the concept in the discussion about the relationship. What is the relationship? Because that's what we want to look at when we look at two variables. What is the relationship between missed classes and final grade? What do we hypothesize in advance? A student that missed classes, or the more classes a student misses, the lower their final grade. So that might be a hypothesis. Now here's the question. Besides answering or looking at that, the question would be, does missing a class cause a grade or influence a grade? In this case, does it cause it, with my hypothesis, does it cause it to be lower? Does not being physically in the class at the time, in the case of even a remote learning experience, just missing the class when it's being delivered, does that cause the final grade to be lower? We have to be careful, even if we did see a relationship. Let's say we actually plotted that and we saw a relationship that did look like the more classes missed, where X is the missed classes and Y is the final grade, it looks like the more classes missed, the grade goes down. So as you go this way, Y goes lower and lower and lower. So a way that we look at that, well, I'll talk more about how we see that's a negative relationship. So is it missing the classes that causes the grade to go down? That's what I want to discuss right now. Well, it could be, but it also could be something else. It could be the case that a person misses classes because they're otherwise occupied. They have other jobs that they're employed in. They have a family, they have family responsibilities. They just don't make it to class. And at the same time they don't make it to class, they also don't manage to sit down and study. They don't have time to study. They're not organized with their studies. And that could be influencing their grade adversely. But not missing classes alone. Missing classes in this scenario is more like a proxy that something's going on. So if you wanted to rectify or correct, you could use attendance to identify students that you might want to communicate with if you're an instructor or trainer, and and intervene, find out what, whether by missing classes there's something else going on. So what am I getting at? I'm getting at the fact that there might be a lurking variable. Okay, a lurking variable is a variable that has an important effect on the relationship or association among variables, but is not included among the variable studies. So what you would want to do is dig a little more, look for other data, or investigate to find out what's really behind the effect that you're seeing. So if you just see a graph like this, without knowing anything more, all you can say is X is associated with Y, but you can't imply that there's a causal effect. So that was my first example. Okay, I'm going to get back and I'm going to ask you again, how many of you, okay, I'll ask it in the positive. How many of you guys want this review? Because this is back in Unit 2. How many of you want me to continue and do this review? Let's see, if I get 10 people saying they want the review, I'll continue. Otherwise, I'm going to jump to Unit 3. So Ileana asked me, could there be lurking variables because a student can miss a few classes but still be diligent? Exactly. Could be diligent, catch up on material, and they have their own pattern. That could happen as well, for sure. So it wouldn't mean that missing classes causes definitively the lower grade. And so that would not have a negative relationship at all. So if 10 of you say you want the review, I'm going to continue. I need some feedback. Just 2 of you? 3? Keep telling me because I need to be incentivized to do this. Anybody else? So the question is, do you want me to continue with the review? Okay. So here I say that my summary, if one was to study the effect of the number of missed classes on final grade received, a possible lurking variable would be studiousness. That is, since people who miss classes are not as studious as those who attend, maybe really what's at issue is the studiousness. So that's even another possibility. So you really wouldn't be testing the effect of attending class on final grade. It is likely instead that you're testing the influence of studiousness on final grade and should be clear about what exactly your explanatory variable is. So it wouldn't be that missing classes causes you, but missing classes acts like a proxy. We call it like a proxy. For something that's hard to measure, you know, studiousness. Unfortunately, we can only study things we can measure. That says, missed classes would be a proxy for a variable that is difficult to measure. Studiousness. Okay, another example. When I was younger, I had a friend who was very influenced by the marketing on cereal boxes. And he was pretty sure, confident that eating cornflakes would make him give him a greater height. So he was intent, on regularly eating his cornflakes. They would have the cornflakes commercials with basketball players as well, so that would work on people's, on their minds and suggest that there was some sort of association, or not just an association, a causal effect of eating cornflakes. In this scenario, is it cornflakes that could possibly make basketball players taller, or children taller? If anything, that is influencing height, it's possibly the milk that's consumed rather than the cornflakes, right? So I begin my example with an example looking at cups of milk consumed and height, just some numbers I made up. And we discuss that data. We're going to discuss it. We're going to look at the data in a scatter plot and discuss whether there's a relationship between the explanatory and the response variable. In this case, the explanatory variable would be the cups of milk, and the response variable would be the height of children. When we talk about correlation in this class, we focus on the linear relationship between two variables. A linear relationship is such that all the observations or all of the values related between the explanatory and the response are related in the same way. You can get from one to another using a slope parameter. Okay, that's a linear relationship. So that's what we're going to focus on. That would be different than looking at, let's say, a curve relationship or other types of relationships that we'll discuss. So just a warning again, even though we might see an association or a pattern, it doesn't mean that one variable caused the other. The only way we can attribute causation is with the gold standard of tests that we learned about, the experimental type study. Okay, so simply because we see a positive correlation or association between average cups of milk consumed in a week and the height of children does not mean that the more milk consumed by the taller children is what caused them to be taller. Findings of strong association from a number of sources or experimental data alone can prove causation. All right, so here's the data that I gave you. And I ask you to plot the data in a scatter plot. So these are the variables, sorry, this is variable X, these are the observations. This is variable Y, and these come in pairs. So when a child drinks 14 cups of milk on average a week, that child turned out to be 60 inches tall at age 11. No, age 10. And so on. So if you put this on a graph, or a chart, or a axis, notice when I'm drawing this, I want to go between, for X, I want to go between the low of 2 and a high of 14. So keep that in mind. So in this space, if this was 15, and then this is 5 and 10, oops. So just to show you how I would do this, I divide this like evenly by 5s. Now this is just a sketch, it's not going to be perfect. You can do this on graph paper if you like to get it right, get a feel for this. And on the other axis, I need to go between low of 42 and a high of 60. So that's like 18 numbers. So I can still use going by 5, right? I could go, so 5, 10, 15, 20, okay. However, I'm going to start at a higher number. I'm going to use a break in the axis so I can start at 40 comfortably, and then this is 45, and this is 50. Oh no, that's not good. I'm going to start at, do that again. I'm going to start at 45, 50, 55, and 60 up here. And I'm just going to do this sketch with red. So when X is 14, Y is 60. So X is 14, Y is 60, it's going to be up here. So I'll put a dot there. Now you can use a piece of paper in a corner, like the corner of a sheet of paper, to help guide your drawing, your sketching. 10 and 60, so that's going to be 10 and 60, be about there, and then 8 and 48, so 8 and 48 would be about here. You can complain if you think my sketch is really off, but this is just to get a general pattern. 2 and 42, 2 and 42 would be like here, and then 6 and 47, 6 and 47 would be like there, and 9 and 55, 9 and 55. So, you know, this is a back of the envelope drawing, just a sketch, and you see there's a pattern. The pattern demonstrates that as x goes up, so does y. Now let me take a moment to show you how I look at this. If you guys can see my yellow line, what I'm going to do is I'm going to divide the x-axis in half. Or what I'm really doing is dividing it in 2 halves using the mean as the center, right? Because statistics is about averages and relative measures, and this is a really great example of that. So what I'm going to do is divide, let's say the mean is about, you know, around here. So this marks the mean, let's say. So x bar would be about there. And then in the other direction, the mean of y is about there, let's say. And what we see by dividing up the data into 4 quadrants in the scatter plot, now I can talk about each observation as either being high relative to the mean or low relative to the mean. So I can say when x is above its mean, which quadrant is y in? Ileana just asked, would you have to confirm that the subject consumes cornflakes with milk, or would that just be an assumption? So for this, we're just looking at the milk. But yeah, if the because some people eat cornflakes just like that, right? But yeah, if to test my hypothesis that it's not the cornflakes that's making kids tall, I would have to make sure. But in this case, I'm just looking at milk for this example, if you didn't notice. So I'm not looking at cornflakes, just milk. Okay, so the question was, when x is above its mean, where does y fall? Which quadrant, high or low? I'll make this bigger if that's hard to see. So when x is above its mean, where is y? High or low? High quadrant. You see that? It's all up here. All the observations are up here. When x is below its mean, so when the values of x are below x bar, where does y happen to be? In the high or the low quadrant? So we say when x high, y is high. When x low, y is where? Hector tells us low. So all I've done, so just to repeat, I've divided the data into 2, and every single observation can be referred to as high or low. So when x is above its mean, y is above its mean. When x is below its mean, y is below its mean. They reinforce each other, okay? And that turns out to be a positive relationship. So we can comment that this relationship is positive. You can consider it linear if you can see that a line could be drawn between these points that could approximate each of the values, and the observations, or sorry, the other values in between that there are no observations for, okay? So this is a positive relationship. We could say it's a linear relationship. We could call it a moderate linear relationship. And that takes care of that. So this moderate refers to the strength of the relationship, how close the observations would be on any line that I could use to substitute the dots. It's linear as opposed to anything else, and it's positive. So these are the comments we want to make when we look at the scatter plot. Remember, when we are looking at one variable, the comments we had to make were all about the 5 features. Sorry, I don't want to make you seasick when I move this around. I haven't figured out how to do that without jiggling the screen too much. Okay, so what we've just done is we've answered question 1. Create a scatter plot of height versus cups of milk. Notice I say height versus cups of milk. This means the first one is always the y versus the second one is always x. Okay, so we say y against x or height against cups of milk. It's just the terminology we use. Is the relationship linear? Yes. Is it weak or strong? We say it's moderate. Is it positive or negative? It's positive. So we've taken care of that. Any questions? So I did that all. That already. Okay. So we need to make a scatter plot before anything's done. And then we look at the overall pattern to identify regularities and curiosities. Identify where there's a regular pattern and where there's deviations from the pattern. Secondly, describe that overall pattern, its form, whether it's linear or non-linear, whether it's a strong relationship, and the direction of the relationship. If the relationship appears to be linear, then we can use tools developed in our statistics class to calculate what's called the correlation coefficient. So this would be the statistic that we would calculate in the event that we see a linear relationship. Then we use the R that we calculate to actually find that line, that special line. Alternatively, the relationship could turn out to be curved or clustered. A curved relationship, maybe like this, it's a relationship. And this is a perfect relationship. It's a perfect curve. I could find the equation of a curve to replace those points and use it to make estimations where I don't have observations. Remember, these are just single observations. What if I wanted to know about, well, let's go back to this for a second. And then I'll go back to that one. So here, this was the example of height versus cups of milk. Now, let's say I wanted to know something about what if a child drinks 16 or 18 cups of milk? So we're going to do some estimation. What if X was 18? Now clearly it's not in my data set. 18 is off outside the range of the data. What about when X equals 11? Which estimation would I feel more comfortable, should I feel more comfortable making? I'll even go a little further. Let's go even further out so we can make this clear. No. I'm going to make this not 18, let's say 20. It's further out. So which one do I feel more comfortable? Should I feel more comfortable making? I would feel more comfortable making an estimation using X equals 11. What I would do is try and find this line, the best fit. The line that fits closest to all the points would be the best line. So let's say that was the best fit line. Or we call it the least squares regression line, and I'll explain why. Let me just say prediction line. I'll say prediction. I don't want to teach you so much terminology. You might get confused. Prediction line. And then using that line, instead of the points, in place of the points, I could trace with the equation of the line and find that value. That's the idea for X equals 11. That's our goal. So I feel comfortable about X equals 11 because it's in the range of the data I've observed. If I go too far outside of that range, it might be inappropriate to even use the line. Could drinking more and more milk really make you more and more tall? You already see in the data as I've given it to you here, this observation doesn't continue going up. Right? The pattern isn't a steady inclination. It flattens out. After some point, it's likely that you can only do so much by drinking milk. There's genetics and there's limitations to your height, right? So a good diet is a good. It helps your bones grow, but to a point. What if X was equal to 50? What about a child drinking 50 cups of milk? Can they be, so much taller? Are they going to end up way over here? Likely not. But we don't know. We actually don't know because we don't have that data. We just have this data over here. So any kind of calculations outside the range of data is known as extrapolation, and you should be wary of making predictions way outside. So I'm going to make a note and say that here. I'm going to say be careful of extrapolation. So students often ask me, well, how far is too far? And that depends on the data set and the variation of that data set. If it's much more spread out, you can go a little bit further, I guess. If it's a much tighter, you don't want to go, you want to stay close to it, right? So, yeah, it depends on the variation. And it can depend on just the variable itself and how it behaves. There might not be any data that exists outside that range. So you wouldn't want to be doing that. You can't see that. So be careful using the line to make predictions. That's all I want to say for now. Yeah, so, you know, in the first unit of the class, we learned about collecting data, and then we just move on from there. So every time I give you data, assume it was collected in a representative way, okay? But yes, it's good data. Our data is good data. All right. So what I was saying over here, what if I wanted to make a prediction, just like with this curve? So if I actually found the equation of a curve, and then I wanted to make a prediction within the range, I could find out what y is when x was a certain value using the equation of the curve. Now we're not gonna focus on equations of curves, but it's not a difficult thing to do once you've got the equation. It turns out if I have some more data, let's say I have some more data and more data, you know, if you were to do the same thing I did in the other exercise and divide the data in half through the x, so let's say this is the average of the x's, and this is the average, well, let me do that again. Let's go a little bit. Let's say that's the average of the y's. And what do we see? Okay, let's see. When x is high, where is y? Well, there's two observations here. You can see them. And there's two observations here. There's one right on the line. So how can we conclude in that case? When x is high, we would say y is indeterminate. We don't know. It can be high or it can be low. Right? When x is low, below its mean, y is both high and low. When that happens, if you don't have a graph, you wouldn't know that there was a relationship here. You would just, you know, if you just had numbers, right? If you just had put these numbers into your computer or the calculator that I'm going to teach you, and you calculate this coefficient r, which we're going to talk about in a second, you would actually get an R of 0 or close to 0, and that would indicate there's no relationship, but that's wrong. There actually is a relationship here. It's a curve relationship, but because of the type of curve it is, it would make an R be 0. So we actually have to draw first before we can do anything, before we can calculate any statistics. And what we would conclude with after seeing this graph, we would comment, we would say there is a relationship. It's called a non-linear relationship. Okay? Similarly, if we had some data, and let's say it looked like this. So there's my graph. We have to comment now. What is the overall form of the relationship, linear or non-linear? What would you say? Okay, Hector says non-linear. Any other comments? Non-linear, Gabrielle. Well, I see some lines. I see a line here. Oh, that's not a very good line. Let me draw it again. Now it's confusing because I split the data in parts, in two, and I see a line, so I need to explain what I'm doing there. I also see a line here. It's not a good fit to the line, but there's a line here too. Or maybe it's less steep. Maybe it's more like this. This is fun because I can just wipe things away very quickly using my iPad. Right. All right, so how do we respond to the question, linear or non-linear? Well, we say the relationship is a cluster relationship. So you have to graph this first. You would see these clusters, right? And you'd say, okay, it's cluster relationship, linear within the clusters. It's a strong linear. I could say moderate. Let's say moderate again. Moderate, linear, and negative. When x is high, y is low. When x is low, y is high. It's an opposite relationship. So what you would have to do is divide the data and estimate those lines, as Hector mentioned, independently, without regard for the other line. Now, how could this happen? Well, this could be a phenomenon where the relationship is the same, between X and Y, notice, because it's negative. However, within, between the two groups, this group is lower in X and this is higher in X. So I use an example in the notes. And I say this is, let's say this was, X was a number of hours watching novelas. So the number of hours watching soap operas, really. And on this axis, the y-axis, let's say we were able to measure using a survey well-being. So we have an index that we calculate asking several questions on a survey to capture well-being. Okay, so there's many surveys that do that. Some better than the others. And it turns out, how do we interpret this? The more hours of soap operas, the less happy an individual is, either in group 1 or in group 2. It's just that group 2 watches more novellas than group 1. So the groups could be, if you did some investigation, it could turn out that these were women and these were men. It could be. I just made this up. Okay? And back to the original statements I made at the beginning of the class, we can't say that watching soap operas makes you depressed. That's not what this says. This just shows that there's an association between hours of watching novellas and state of well-being. So it could be explained by the fact that people who are either alone, isolated, unwell, handicapped, they're just at home watching novellas, okay? And that could explain, and women tend to watch more of them, men not so much. Not as much as women anyway. Okay, so I've said a lot in this drawing. What I really want you to get from here really is that you need to graph your data first before you do anything, because everything that comes subsequent is a matter of how you're going to divide the data and analyze it. You can't just put the numbers in your computer and get analysis out of it. Okay, that's not correct. You need to visualize the data. Right? So, if we had put this in our computer and asked, or even our calculator, okay, which I'm going to show you how to do, and you asked for the information on the regression line or the line, it would have shown you what? This yellow, would have given you the yellow line, and it would be wrong. It would be a terrible fit, like really bad scatter, huge gap here, and big scatter. The points are not fitting on this line, and the line is positively sloped, so it's completely wrong. It's implying that the more soap opera hours you watch, the happier you are, and we definitely don't want to convey that information. I'm really an advocate for not watching soap operas. There's nothing I can do. My mom's addicted to Spanish soap operas, and hence the example. She's not that bad. She just watches them at night, but I think it's too much. My dad watches them now too. All right, so let's get rid of that yellow line because it's not the right line. Okay, questions, comments? Okay, so now we're going to get into the R, okay? And you notice if you read these notes already, I itemize each of the types of questions I ask, so you realize, you're preparing for the test in this way. There's only 9 kind of questions that I ask you. And the first one is those 3 things: the form, the strength, and the direction of the scatter plot of data. The second question is, can we predict using the R that we calculate? Can we predict Y from X? So we need R. We begin with R. The R is the correlation coefficient. It's a measure, so it replaces, just like we did in univariate when we looked at one variable, just like the 5-number summary replaces the graph. It stands in for the graph, but it's all statistical commentary. Similarly, the correlation coefficient, if there is a linear relationship between 2 quantitative variables, you can use the correlation coefficient and it will tell you the direction and strength of the linear relationship between those 2 quantitative variables. The R will always be between -1 and 1. 0 is an indication of no relationship. All right, so this might be a little bit different than I did it before. Maybe I should pull that up. Let me get what I did before so it looks the same. Okay, so what I said, what if you have this as your relationship, your scatter plot? What would the R be? So the range of R it goes from -1 to 1. So the most positive it could be is the strongest it could be. So this is strong in the sense that let me check something. Oh, I'm a little bit off. It falls perfectly on that line. All right? That is an R of +1. That's the best you can get for R. The strength is denoted by how close to +1 R is. So that's different from, what if I did this? So now R is not +1, but it's close to +1. So it probably, and we're going to learn how to calculate it, it'll probably be +0.8 or something like that. Okay, so close to the line, but not all exactly on a line. So the line that would estimate that should be only drawn around the range of the data and closest to all of the points, floating in the middle of them. And as there's more or less of a relationship, the data is just scattered around like this. So this is an example of R being close to 0. If I saw a little bit of a trend, you know, if it was like just, you know, really low down here, now I start to see a more positive pattern, but it's still going to be close to 0, so maybe 0. Let's say 0.1. Okay. Now, on the other end, data could be like this. And here, data, so I don't know that I did this enough. Let's say we divided the data in half. So let's say we divide it in half this way. This is the mean, and then we divide it in half this way. This is the mean of, well, I'll do it again. So what do we say here? When x is above its mean, y is low, right? So when x is high, y is low. That's an opposite relationship. And then it's confirmed on the other side as well. When x is low, y is high rather than low. So this is a negative relationship, and if it's consistent, they're opposite. You know, they do the opposite thing, and if they do it perfectly opposite, what you get is an R of -1. I can be less close to the line like that, but it's still negative. But it's starting to get closer to 0. So it's -0.6, let's say. Finally, we could have a relationship like this. It shows a pattern, but it's not a line. And a line could be used, but it wouldn't be the greatest at making predictions in some ranges. So if I used a line over here, I couldn't use a line over here. Well, I can maybe use this line, but then over here, what would I do? So it's best for making predictions to estimate using a curve. And like I say, we're not going to learn that now, but it's easy enough to, we're going to focus on the line, and then I gave you some notes that you can read so you can learn how to do all kinds of other shapes or relationships. Okay, so if we were to try and calculate the R of this relationship, you shouldn't calculate R for this, right? This is a non-linear relationship. If you did compute R, you'd see it would show you R is close to 0, but that's not exactly the right way to use R. Comments? And that's it. Then I have some exercises. So there's your review, and you guys, if you want to see that again, you can watch this video, or you can watch the videos I mentioned at the beginning. Videos. I had to sneeze. Videos 17, 18, 19, 48, 49, 50. Okay, that's what we're going to talk about next. Okay, so let's go to that. Any questions about this? Everybody's okay? So we're going to get deeper into R. I gotta find out how to open that so that the files appear larger. Right off the bat, I mentioned to you that you don't have to read. This is a very short chapter or unit. You don't have to worry about unit pages 13 to 18. That's if you want to look more into different types of relationships and how to transform the data so you can still use linear regression, which is what we're going to learn, to estimate that relationship, okay? So we're going to focus now on the sample correlation coefficient R and making calculations. Just turning up. I'm here. I'm just getting comfortable. Okay. So what is the sample correlation R? R is a statistic, right? Because it's calculated, too far from the microphone, I think. R is calculated from the data. So it's from the data, from your sample. So it's a statistic. It's the statistic R. Let me show you this. Now remember, all the statistics estimate a parameter, right? So what's the parameter it estimates? It's a Greek letter, and it looks like a P, but in Greek this is an R. Rho. It's a Greek letter R. You're going to see that symbol again, so that's what I'm showing you now. So it's a statistic since it is a number calculated from a sample of pairs of data now. It's still data. It measures the direction as seen as in its sign and the strength as seen in its magnitude between -1 and 1. Only for a linear relationship between two quantitative variables. So it's very important, quantitative, right? We learned about quantitative variables. Those are numbers, values that are objectively measured, that you can calculate meaningful averages for. So in other words, it's not a qualitative or categorical variable. So for instance, you cannot compute correlation, well, not this kind of correlation, not the linear correlation. You cannot compute correlation R between something like income, which is quantitative, and gender, which is categorical. You would do something else, some other sort of calculation, but not this R, to capture correlation. All right? So this is the formula for R. We're going to look at it. When you look at it, what do you see? Ooh, sorry. Hope no one's getting seasick, really. Motion sick. What do you see here? What do you recognize? What do you see? Okay, so you're seeing you recognize the means, and you recognize the standard deviations of the sample, right? But what do you see in the big picture? What are we staring at here? And there's something else you should see here too. Okay, what do we call this? What did I tell you when you see this? What you should see? Okay, but what about this part? So this is a sort of average. Again, statistics is about averages and relative measures. If you see it at the beginning, or if you know that, you'll keep seeing it, okay? So this is like an average of what's in here? What is this in here? It's the mean, the standard deviation, but what is this thing in the brackets? Somebody, what do you see? Doesn't this look like what do we call that? what do we call this? Right, standardization. What this does is it converts every value relative to its mean in terms of standard deviation. So it converts every value to the number of standard deviations it is from the mean, every value for x, and its pair, every value for y. Okay, so x and y are standardized, then they're multiplied and averaged. So we are replicating the visualization I did before, looking values above the mean and below the mean. What happens to x when, what happens to y when x is above its mean? Is it above or below? It's all being captured in this by relating and standardizing relative to the mean for each of the values. Look what's going to happen here. When x is above its mean, so when when the relationship is positive, right? R should be positive. Okay, and the degree to which it's positive, or the magnitude or the strength of that relationship, depends on how precise, how well y mimics x. When x is above its mean, this will be positive, right? Because if x is above its mean, it's going to be higher than minus, if I subtract off the mean, and then you standardize it, that's going to be a positive. So this whole term will be a positive. If y behaves the same way, then when y is above its mean, the standardized term will be positive. So we'll be multiplying a positive times a positive. And if we keep doing that because it keeps on happening, then we're going to be adding a bunch of positives into our total before we average. That's what's going to create a positive R. What about when x is negative, though? So with a positive relationship, remember, this is really important. Let's say x is low. So let's say x is below its mean. So if x is below its mean, x minus the mean will be a negative number, which is standardized as will always be positive, right? The standard deviation is always positive. Why? Because it's always positive, because it's the square root of something. So don't forget that. So when x is below its mean, this term will be negative, but then if it's a positive relationship, y will also be below its mean in the pair. But it turns out, if I multiply a negative and a negative, what do I get? Negative times a negative also makes a positive. So I'm adding more positives and reinforcing R being positive. Okay, so a positive relationship is reinforced with this multiplication. I'm just adding a bunch of positives together. What about a negative relationship? If you guys don't get this, I'm going to do this again anyway, so don't worry about too much. For a negative relationship, R will be less than 0. How can I see that? Okay, so let's say if x is above its mean, if the relationship is negative, then y would be below its mean, you see? And then a positive times a negative will be a negative. If this keeps on happening because it's a negative relationship, then I'm just going to be adding a bunch of negatives together and R will end up being negative. if it's a negative relationship and x is below its mean, y will be above its mean. That will also make a multiplication, that will also multiply to be a negative, adding more negatives, reinforcing this negative, r being negative. All right, so that's what that's what we have here, an average. So, how is r interpreted? Besides indicating the linear correlation between two quantitative variables, r is used in practice to help make predictions of the value of the response variable from a value of the explanatory variable. That's how we use r. So it's very important. Just some points about r that you need to know before we get into making calculations. In calculating r, let me show you with the formula visible. Clean it up. Notice x is treated the same as y is treated, X is treated the same as y is treated, right? It's standardized. So in calculating r, it doesn't really matter which variable I call x and which one I call y. However, when I need to make the line, that's when it matters which one is x and which one is y, okay? So there's no distinction between explanatory and response variable x or y unless specifically instructed to plot one variable versus the other. This is the same as saying that one does not cause the other, so it doesn't matter which is which. And then I restate that. Just because variables move in the same direction doesn't mean that they're causal, or they tend in repeated observations to behave either in reinforcing each other. When one is high, the other one is high, and the one is low, the other one is low, or opposite. Doesn't mean that one is causing the other to move that way. You'd have to prove that. It's just an association that we interpret. Okay, second point. To do any of this, your variables must be quantitative, not categorical. Both of them must be quantitative. Next point, 3. R has no unit of measure. Notice I say R. I didn't say R%. I didn't say R. I didn't use any units for R. Okay? So R is just an index. So I give you an example where we're measuring in millimeters. We're going to do this example in a moment. Notice that to get R, we standardize this term. Well, a value minus its mean would be millimeters minus millimeters, and its standard deviation would also be in millimeters as a unit. So those the units would cancel because you'd have the same on top and on the bottom, leaving just the values. Okay, so this is the idea of an index. This is an index. There's no units. It's an index interpreted between -1 and 1. Direction we've already talked about, just to summarize. You could have R as positive, where two variables are positively associated when one above average values. When above average values of one tend to accompany above average values of the other, and below average values of one accompany below average values of the other. the relationship is negative when above average values of one tend to accompany below average values of the other, and this is consistent in the other direction as well. Below average values of one accompany above average values of the other. Strength, we've already discussed this. So R is between -1 and 1. R equals 0 is no relationship. The most positive would be on a perfect line. In that case, R would be 1. So the magnitude of R tells you how well the observations fit on a line. So they perfectly fit on a line with a positive slope. If R equals -1, they perfectly fit on a line with a negative slope. Sixth point, R only measures the strength and direction of a linear relationship, not a curved or clustered relationship, no matter how close values fit this other pattern. 7. This is the last plot I'm going to do. So say this was your data. So for this, we can go back to the example of milk, drinking milk. The more milk you drink, it's a positive relationship. The more milk children drink, the taller they are. But what if I got an observation? I happen to have a really, I used data or presented data in this range. I'm trying to make it a straight line. Okay. But it turns out that I have another data point, but it's over here. So this reflects the notion that, after some point, drinking more milk can't affect your height, okay? Because there's just physical limits on your genetics. What would this do to the prediction line? If I was forced to include that point, I will use a dashed line, and the principle of the prediction line is the prediction line needs to float between, closest to between, or being, it floats between the points, and that way it's closest to all the points. So it would have to fall like this to include that point. So that affects there's a new slope and new intercept. It affects the line completely. Remember what is slope and all this stuff. Let me write it down. Y equals a plus bx. Right, so this is the slope, and this is the y-intercept. And both of those are going to change to include that point. The other thing that's going to change is the r. the r is going to get destroyed. It's going to be closer to 0 than what it was before. So we call this point that affected our line so much, this point is called an influential point. It's like an outlier, but in the vocabulary of scatterplots and linear regression, which is what we're talking about here, it has a special name and it's called an influential point. Now this happens because of the, think about the equation of the line. So R, remember, R is equal to 1, it's the average, the sort of average of this multiplication of these standardized values. Look at this. The fact is, R depends on X bar. And what do we know about X bar? It's sensitive to outliers, right? Also, S is sensitive to outliers. So R is sensitive to outliers. And that's your example there. So you have to be clear that any values that appear to be influential, that you really do want to include them, because they will mess up the quality or the efficiency of your prediction line to predict, right? So basically it's not going to be as good using this line to predict values over here. So we have to figure out what to do. Okay, we can either measure some sort of curve, maybe there's a curve relationship that would better represent the data, or we just use the line in this range and see that there's a saturation point. So we'd just be at like a plateau this way. So we'd have to figure that out. But as far as you're concerned, you just need to know that that influential point will affect your fit to the line, the R, and it will change your line, your prediction line. Questions so far? So a question that people often ask is do I have a relationship? So I see a scatter plot, and can you conclude that there's a relationship there? So this number 8 is just a rule of thumb I came by to help people looking at scatter plots to make those kinds of assessments. This means that you can attribute a relationship between the variables as long as this is true. So let's see, what does this mean? Let's say n equals 100 observations, then this would mean that R has to be greater than or equal to 2 over 10 or 0.2. So this means that to have a relationship, to be able to say there's a relationship, R greater than or equal to 0.2, or R, because if it's a negative, right, R less than negative 0.2, in either of those cases, you could say you have a relationship, which is really pretty amazing. Your R does not have to be so close to 1 to be able to say you have a relationship. That's how you interpret that. Okay, so The last point to make in this overview is to say that provided the scatter plot and calculation of R reveals a strong linear relationship, we can use R to estimate what's called the least squares regression line that is useful for prediction and estimation purposes. Okay, what I want to do now is 741. I'm going to jump over all these notes. I'm going to teach you how to make these calculations in your calculator. And then with the time remaining, I'm going to show you where the formulas come from. Okay? Actually, you know what? I'm just going to use this example first, and then I'll do the big jump to the rest. So here's this example here. Let's use this example in our calculators to get the results. The question states there should be a strong linear relationship between the length in millimeters of pairs of bones, the leg bone and the arm bone, from 5 fossils of prehistoric insects. So what we're going to see, if an insect is big or small, still the proportion between their leg and their arm length should be the same from insect to insect. So we're going to check if these pairs fall in the line. Basically, do they have the same proportion between them? So even if their high is one just like 2 or 1.5 times the other, that's what we're going to look for. So in that case, the leg bone, this is a good example because it doesn't really matter which one is X and which one is Y, right? We're not saying that the leg bone is causing the arm bone to be a certain length. So the use of the terminology independent and dependent is just to make our drawing, but we're not implying that one causes the other. So in this example, I ask you to plot, and I tell you to plot in a particular way. I ask for humerus versus femur. So arm versus leg. Okay, so so humerus has to be on the Y. And femur has to be on the X. Okay? And I asked you to plot the data first and comment. And when you plot it, you'll see it's kind of like this, I think, something like that. So just going back an instant. So this means this is X and this is Y. No, is that right? No, the other way around. This is humerus versus femur. So this is Y and this is X. So I usually do that. I put down the X and Y at the beginning because it does matter when you make the line. It doesn't matter in calculating R, but it matters for the line. So if we took our calculators and put these numbers in, let's see if I can demonstrate with my calculator. See what happens if I do this. Is it gonna wipe out No, it won't let me do both. Okay, no, I have to show you on this. So let's see, I'm going to pull up the calculator. Just got to get the numbers. Okay, the calculator. Okay, so what we want to use, remember second data. Now there's numbers in there already. So I say second clear work. So you can do this in Excel. You can use your calculator in stat mode, whatever calculator you have. No one's asked me to help them with their calculator, so I figure you know what you're doing, but if you don't, we'll find out now. So pull out your calculator, I'll give you a minute. Let's take a 5-minute break so you can get your calculator or get organized and get a glass of water, a cup of water, and we'll continue, okay? So 5 minutes, take 5 minutes. All right, I'm back. I am back. Everybody back? So what I want to do is take these numbers. The femur is X and humerus is Y. So what I'm going to do is enter 38, enter, down. Now I'm going to enter the Y. 41, excuse me, I have hiccups. Enter, down. Next observation. The second observation, 56, enter, down. 63, enter, down. 59, enter, down. 70, enter, down. Fourth observation, 64, enter, down. 72, enter, down. One more. 74, enter, down. And 84, enter, down. There you go. I have all the observations, all the data. Anybody need me to do it again? So now I can ask the calculator to compute. So second stat, that's the statistical data, and it says lin. Lin for linear, okay? So linear, these are the linear estimates. It's going to show you that n is 5, so that's the number of observations. So I'm going to show you now, and I'll do this again, okay? So you get to see it again. N is 5. This is the mean, 58.2 for X. This is the standard deviation for X, 13.2. And remember, this is the population standard deviation, which we do not use that one, right? Because we are just working with samples. This is the sample mean Y. This is its standard deviation. This one we don't pay attention to because that's as though it was a population, but we know we have a sample, so we use SY. And now here's the fun part. What is this? What do we have here? What is that? What is that? And what is that? It's everything I want, right? That's my R. It's 0.99, which is almost perfect. It's almost 1. This is the slope of the line, the linear regression line that fits closest to all the points, that passes through the range of data. And this is the y-intercept. It's all there in the calculator. So that's why I tell you to get this calculator, because it just makes everything so simple and handy. A lot more complex than any other place, really, I think. You have to open a computer and get it in Excel and make a list. I don't know. This seems just so easy. Other calculators equally as easy. You just got to figure out how to use them, okay? So now that I've shown you on the calculator, I can expect a lot from you. I don't expect you to make all these calculations in the tables that I'm going to show you now every time. What I expect is you to use your calculator. I might want you to demonstrate that you understand the tables, and the table method I'm going to show you helps to illustrate what the R calculation is capturing. But really, efficiently, you can just get the numbers out of your calculator like this. All right, so let's see if we saw those numbers. Okay, let's, what I'm going to do, we have to comment on this, right? I didn't comment yet. So we just saw the results. I didn't even write them down, but they're in my calculator, so we can go back and confirm when we're done. And like I said, I'll show you how to use a calculator in a bit, once we get through this. Okay, is the relationship linear? Yes, I see a line here. I see there could be a line that substitutes for those points, right? And it's linear, yes, so I'm going to say linear, strong, and positive. Calculate R. So we calculated R in our calculator and we got R 0.99. So are these fossils likely to be from the same species? We say yes, right? Because they have the same relationship, the same proportion. Now what is that proportion? Well, that would be given by the slope of that line. So can we now use this relationship to predict what the arm bone's length can be predicted from the leg bone? Okay, so we're using the leg to predict the arm, and it looks like, you know, on these insects, their arms are much longer. So we're going to say yes, because the R is strong, the fit is strong, and it makes sense to use this line because we're going to get close. For instance, if I don't have data here, but I want to make a prediction here, I'm going to predict from this value, I can find this Y on the line. How good would the line be? Well, look here. In this case, this is actually an observation. So it's not exactly on the line. There's some error there, okay? And that needs to be taken into account. That influences the best fit line, right? We want the line to fit closest to all the points so that there's not this error, that I'm not off in my any predictions. When I don't have data, I wouldn't be able to compare that, but I use the other observations to give me an idea of how good that line is. All right, so let's do the calculations manually for once, so I can illustrate what the R does yet again. So here's the data, here's the table, and you recognize these numbers. This is the mean of X and its standard deviation. This is the mean of Y and its standard deviation. There's n observations, 5 observations. So standardizing X, first we need the mean. So we have that already. You see, I give it to you to make this easier. So what we're going to do is take each value, standardize it, take off the mean and divide by the standard deviation. Now obviously, you know, we're just using the sample results to do that, but I still call it standardization because that's what it is. So implicit in everything we're doing is the idea that our data should be, right, symmetric. The X distribution should be symmetric. The Y distribution should be symmetric. If they're not, then we're going to have outliers, right? And or extreme values outside the pattern, and that will make our prediction lines weak. Not that great at making predictions. So let's do this. Let's get the standardized value. So to get that, I'm going to take 38 minus 58.2 divided by 13.19. So that's what I'm going to put in here. And I get this value, negative 1.5 3. I'll just use 2 decimal places. And now I'm going to do it for x. I'm going to take 41 minus 66 divided by 15.89. And I get negative 1.57. Now I can't see you, so you have to tell me. You have to do this, okay? So try that, and then let's talk. Okay, so stop for a moment, and what do we see? What does this say? This says when x is 1.5 standard deviation below its mean, y is also about the same, 1.57 standard deviations below its mean. They're behaving, they're moving in the same relative direction, in the same magnitude. Okay, they're moving the same way. And if I do this all the way down, you'll see that pattern pretty much happens all the way down. Now the tables will be easier to do in Excel for sure, but I don't want you to lose the essence of what's going on. So I'm doing it step by step here. Let me know if I make any mistakes. Now you see, when x is only slightly below its mean, y is only slightly below its mean. Okay, so they do the same thing. They reinforce each other. Okay, here we go. When x is below, it's very close to its mean, right? 59 and 58.2 are very close. Y will also be close to its mean. These are a little more distant than the other ones. They were much closer, but still, it's the same direction and magnitude, relatively speaking. Okay, let me know if I make a mistake. And again, when x is below its mean, this is like 1/2 standard deviation from the mean, then this is about 1/2 standard deviation from the mean, above the mean. And finally, Okay? Again, they're doing the same sort of thing. They're both about the same distance from their mean. All right, so what happens is I'm going to multiply these together now. So when I have a negative times a negative, this is going to end up being a positive. When I have a positive times a positive, it'll be a positive. So this is going to make all these positives all the way down. I do need the number before I get the total, so let's do that. So this is 2.4. 0.03. I'm just rounding to 2 decimal places. 0.06 times 0.25. 0.2. Okay, how's that? Then I total them. And I get 3.98. So then I jump to this step. All I have to do, I've gotten this value. I've done all of this. I just have to get the average. So it's not exactly divide by 5, right? Because I lose a degree of freedom. Why did I lose a degree of freedom? Because of using estimates inside of the estimator. It's because it's in a pair, I only lose 1 degree of freedom. It's not like 2 observations. It's just 1 degree of freedom. Okay, so now I divide that by 4 and I get 0.995 or 1 as my answer. Now what did I have on the calculator? First of all, any questions? Let's go back and look at the calculator. Now remember, the calculator keeps way more decimal places than I did, so it might be a little bit different. What did we get here in the calculator? 0.994. So they held all the decimal places, we rounded, and we ended up a little bit higher as a result. So what does it mean? If you don't have any questions, oh, you got even lower? Okay. So if you do 3.95, you get even lower. Yeah, you 3.95. But anyway, you know, you're going to get the right answer on any kind of test. You did fine. The rule I usually say to use is you keep 2 more decimal places than the actual number. So because these had no decimal places, I kept 2 all the way down. You see? I kept 2. That's what I did. I have a rule in the notes. I wrote it down at the beginning. Keep 2 more decimal places than the original numbers. This is just to ensure you get the numbers I get in my documents. So you're not tearing your hair out that it's wrong or it's not accurate enough, or okay, but this is not really not a statistical standard or like a scientific notation standard. It's just something I use for teaching purposes. So keep 2 more decimal places than the original numbers or values. Let's say values. Okay, so this means that the relationship is as we thought it would be, strong, positive, linear relationship. Okay, so the reason why I like demonstrating with this version of the formula is because you get to see all this, right? It's really important, but I'm not going to do that every time. Don't expect you to do that every time. You should know that now. That's what it does. Another way to calculate this, which I want to emphasize, is with a variation on the formula that you need to know. So I put the tables here for you to try if you have time to, it's actually easier. You can try and use these tables to fill in and get the same answer. And what is this? What do you do with this table? What formula do you use? Okay, so this is what I want to discuss next. So this is the formula that we just used. The version of the formula that we just used is this one. Right? But it could be written like this as well. What is this? Well, if I'm taking, you notice in the tables that we did before, we took x minus x bar divided by s. This number and this number were already calculated. They were pre-calculated. So really, this is just a constant, right? So it's just a constant. Can't I just write this as can I just take those out? Is that okay? Can I do that? So you can, like, I don't know, you can think about it like that, or that this is like an amount that's multiplying by this sum. This is the sum. Those are the same thing. So what this is saying is I did not have to do it this way. I didn't have to take every value and divide it every time by Sx. I just wanted to show you the standardizing process. I could have just subtracted it from the mean, summed them up, and at the end divided by the standard deviation. In other words, I could standardize after doing this. I'm going to write this one more way. Can I just write it like this too? Same thing? Is that the same thing? Same thing. All right. So now I can ask you, this is the standardizing piece. By dividing by the two standard deviations. So then what is this? Is this anything special? Anything recognizable? Anything you've seen before in there? I'm going to write something that looks similar. What's that? Okay, first this question, Hector. What's this thing? I can write it one more way. Can't erase that. What's this? Okay. But what do we call this thing? This is called these are the variance. Right? That's the variance. Right. The variance, remember, the square root of the variance okay, the square root of the variance of x is the standard deviation. So that's what this is. So this is called the variance. So we call this the covariance. So now, if you've never seen this before, I hope you can see the pattern. You know, people say, students say to me, oh, I'm not mathematical, I'm not mathematical. Well, if you're not mathematical, you're probably better visually or verbally or artistically maybe. And so I appeal to you looking for patterns, okay? It's not about numbers, it's patterns. And the pattern here is this is covariance. It looks like this, but I'm taking deviations from the mean of each at the same time and looking at their trend. How do they trend together? And the trick is that if they're both negatives, then they're still trending together because a negative times a negative is a positive. It's a positive relationship. So this tells me a different interpretation of R now. Well, not different, but I guess it's R is what we've been saying is the measure of direction and strength of a linear relationship between two quantitative variables. R is also the standardized covariance. You can think of it like that. So covariance is really the term that gives you, this is the measure of direction I guess and strength too, but it's hard to interpret. It's the measure of the direction and strength of a linear relationship, except from variable to variable, we don't know what a high or low covariance is. So we have two variables, we just don't know from sets of variables how to interpret if a covariance is high or low. So what we do is we standardize, we convert whatever variables you're using, we convert them to a range between -1 and 1. Isn't that interesting? This converts it to a range of -1 and 1. So now we can interpret it with this index. Okay, but I don't want you to forget that R is the standardized covariance. That's all it is. So that's all I say here. All these formulas, just the same thing. This is just this. This is the one we used. This is the same. And then I get here. So this is the notation I use for covariance. I write covariance X, comma, Y. So I don't have to write all of this. So that's what I want you to remember. I want you to remember this. And I want you to remember this. And of course, this over here, what covariance is. Any questions? So it's covariance that's really capturing the measure and the strength of a linear relationship between two quantitative variables, but just don't, you know, it's hard to interpret covariance for variables I'm not familiar with, so I standardize them and convert the measure of covariance into R. All right, so we got another couple of examples. So I'm going to leave for you, if you want to do it or not, for practice. Fill in these tables, get familiar with, you know, doing it this way. Also, I give you another data set to prove to you that this relationship, even though it is, notice we're going to plot mileage as Y and speed as X, that as X goes up, Y goes up and then down. So this is going to be a plot like this, a curve relationship, and I'm going to show you, demonstrate that R will be 0 here. So you can practice doing that on your own. Okay? And I have all the calculations there for you for practice. Any questions? It's 8:24. Okay, so what I want to do, okay, so there, yeah, it's almost 9 o'clock. So what I'm going to tell you to do is watch the videos. Watch the videos, because now these are all videos. This is a video. This is a video explanation, and then I just have a bunch of exercises. So I'm going to ask you to do that. Watch those videos and realize all I'm expecting you to know how to do is 1 to 9. The rest of the stuff, I'm not going to ask you in this class, okay? You just have to know how to do these things. How to make a scatter plot, which you learned how to do. How to comment on the pattern. Is it linear relationship, positive or negative, weak or strong? Find R in the least squares regression line. So that's what you're going to work with the videos. Interpret the slope and the y-intercept. Then use the line to predict x when y when x is a particular value. Find a residual. So that's the kind of error off of the line that you're going to learn about. Determine if a particular value is influential. And then what proportion of the variation in y is explained by x? What is r squared? So I want you to work on these. That's pretty much it. You don't have to worry about these pages either, pages 10, 11, and 12. I put them in there because it's important, but I think, I don't know, we're going to get lost if we can spend a lot of time on regression and we don't really need to. You just need the basics. So all of this, don't worry about it. So I will say up to here. Unless you want to have a greater depth of understanding, you can read the rest. The rest, there's like another like 10 pages. Yeah. And then here, start again on page 19. And here you have a bunch of exercises, practice. Okay. What I'm going to do now, because we do have 15 minutes, and the most important thing, I'm going to skip and just talk about the results of the regression line. Okay? And then you guys can fill in the blanks with the videos. What we're going to do when we come back next week is you should go through all of this. You should read all of this, try all of the exercises, and come with questions. I will highlight a few things, but you should be able to do this all yourself. Solve all of these problems. Okay, you have answers for most of them, and then try the quizzes. And then next week, I guess maybe I'll bring a couple of problems. We can do them together, but you even have problems in Moodle. So try and come prepared and with questions for me. And then next week, I really want to start probability. So maybe we spend a half an hour on this. So let me go back to the results, the line. Now, if you don't know what a line is, you don't remember, or you need the line review, I provide it. So you're going to work with this video on this topic about lines, to remember lines. So that's remedial work. And then here is the most important thing to tell you about, and you'll see a review in the videos when you go through it. So what we're doing when we're trying to capture this line is we're estimating it. Essentially, we want to find this line. But because the points don't all fall on the line, it's just a prediction line. So we use a hat to distinguish statistics from mathematics. And we put a hat here and a hat here, but I don't think I put a hat in all the notes. So, I dropped the hats, these hats in these notes, but really these are all estimates. You're estimating what the intercept is, you're estimating what the slope is, because this is just a sample. And there could be a bunch more observations, and for the whole population, you'd actually have a parameter. So this estimates the parameter for the intercept. This estimates the parameter for the slope, and this estimates the true line. Right? So we use the hat to distinguish. Not to be so intimidating, I just get rid of the hats, but really they're estimates. Okay, so the idea of the line is the line fits closest to all the points in that it minimizes the residual. What is the residual? How do we find the line so that you see this distance that I'm drawing, this yellow or this gold? Imagine if I took all those gold, like if this distance, this as like a piece of string, and I took them and I connected them in a long string to represent all of those distances. These are all called residuals. That's what these are. That's what that is. It's a residual. You take the observed value of y, so that's the y value here. Okay, they should be straight up and down. It's a little bit, oh dear. They're a little bit crooked. Maybe you can't see them. Let me do it again because you can't see. So this should be, you know, okay. Whatever the y value is, that is actually a value that was measured. And whatever the line would provide for that measure of the explanatory variable if I took the y of the observed value and then the predicted value on the line, that would I would be calculating the residual. Okay, so that's the error, how far off the line was at predicting that observation. You can also write the predicted value as y hat. So I'm going to do that for all of these for the one line I pick. So let's say I pick this line. I think that's the best line. Then I go and calculate all these residuals. So this sounds like a really tedious exercise, right? There's got to be a better way to do this. And so the fact is there is. Mathematically, I would calculate, mathematically, a computer would be finding the line such that the total of all these residuals was minimized. But before I go to talking about those results, I want you to realize the residuals on the top, what would they be, positive or negative? The residuals above the line. The residuals above the line would be positive. The residuals below the line would be negative. So if I was to actually use the residuals, I would have positives and negatives. And if this was a good line, this line would fit perfectly floating between these on the top and these on the bottom. So if these were positive and these were negative, and I summed all of those residuals, what would happen? So this feels like when we were working with the deviation, standard deviation, right? We had to square the deviations from the mean to be able to sum them, because the mean was in a position perfectly balancing closest to all the other points. That's what the mean is. It's the balancing point of all of the observations, of the distribution. Similarly, this line floats in such a way that it's floating evenly between all of the points. So if I took all of these residuals, they would be positive, and these residuals negative, and I sum them, I should get 0. So to avoid that, we want to maintain the magnitude of the residual, not the sign. What we do is, just like the standard deviation, is we square them. We square them and we try and find the least squared residual. A line that is such that that we minimize the squared residuals. Okay? So that's why we call it the least squares prediction line, because it's the best line as it fits closest to all of the points. It fits such that it minimizes the sum of the squared residuals. All right, so this is known as ordinary least squares, or OLS estimation of A and B. The parameters are estimated by the estimates for A and B. Now, how do we get A and B? So we're talking about optimization. Optimization is achieved with calculus. So any of you who took calculus, great, and you can appreciate now in graduate school or in higher level courses since high school or first year university, you can appreciate significance in optimization problems. So what you're trying to do is you're trying to find the best, right? You're trying to find the best, and the best is the one that minimizes the squared residuals. Calculus will do this, and there's a pattern to the calculus results that we can use. Now, I'm not going to do calculus here. In another higher level statistics course, you would do calculus, or you would learn about calculus, but we're just going to learn about the results. And the results of calculus are that this line must pass through the point that is closest to all of the points. And that point will be x bar, y bar. X bar, y bar, remember, the mean is the center of gravity. The center of gravity is closest to all the other points, balancing in both directions. And now we're going to balance in both the x and y, horizontal and vertical direction. So this must fall on the line. So that's the first point. The second point, so we have a point. So this is a point. Very important when we're trying to calculate the equation of a line. So after we do this, all I want you to be able to do is interpret these results. I want you to be able to calculate the slope and the line, but I'm really equally concerned about interpretation. So you need to know how to interpret this result. So this is a point on the line. If I have a point and I have a slope, I can estimate the line, or I can calculate the line mathematically. So that's what we're going to do. The challenge is that we have so many observations, we use them to find this best fit line, but we can't use standard mathematics, right? So because we don't know which point to use, but I'm telling you right now, this has to fall on the line, x bar, y bar, and the slope will always be computed this way. This is the formula for the slope of the line. Okay, so this is a result of performing the calculus minimization problem. To remember this, I teach students the mnemonic risk. It's R times SY, the Y comes first, divided by SX. So you need to remember the basic pattern, that is R times SY, or R times the standard deviations, but to remember the order that Y is on top of X, I teach you this mnemonic. And in fact, B, or slope, is a measure of risk if we use some financial data. And I give you an example in the notes so you can see that. So what is the deal here? So R, notice, since S, the two standard deviations are going to be positive. These are positive. This is positive. Remember, the standard deviations are positive because standard deviations are square root of a variance. When a number is a square root of another, it's always going to be positive. So this means, since these are positive, the slope and the R have the same sign. Okay? Okay, so let's talk about what the slope is. So the videos, you have to, watch the videos so you learn about the slopes better, but I'm just going to do the interpretation now. And we can talk about that. So this is the calculation. Now you can't do it the way you would do in mathematics, right? Because you wouldn't know which two, because to calculate a slope, if you have a line, if all of them were on a line, then you would just have to take 2 points and calculate the slope. That's what you would do mathematically, but I don't have them all on the line. They're all over the line, so I wouldn't know which two to pick. So this is how you find the slope, but then the interpretation is the same. I will still interpret this result as the change in Y over change in X. So let's make the calculations, and then we'll make the interpretation before we go today. And then you watch the videos to see more details. Okay, so this is just a result that we're going to use. And finally, I have a point and a slope, so I can calculate the y-intercept by plugging in into the formula, the regular mathematical formula. I have this, and then I could use x bar, y bar, so then I would find A. That's the third point. Find the y-intercept. So that's the third point. So first, x bar, y bar falls on the line because it's the point that's closest to all the other observations. So it has to be on the line that fits closest to all the points. It has to. The slope is found by this fancy formula where I teach you the mnemonic to remember it. Risk, R times SY over SX. Where it comes from is the result of minimizing the squared residuals. And then I have a point and a slope, and with that I can plug into the formula for a line, and I can solve and find the y-intercept. And for the example that we did with my calculator for the arm bone and leg bone relationship, these are the results here. The results are that the two means, if you remember these numbers, this is x bar, this is y bar. That falls on the line. The slope, if I plug in sy over sx, this is the slope. So it shows me that the slope is 1.2. What does that mean? B is 1.2 over 1. It means if, remember x was a leg bone, right? So if the leg bone is one, for each unit, additional unit of leg bone, the arm bone is 1.2 units more. So for each additional x, y is an additional that. So this is a positive relationship. And it's, so the, the leg, I have to remember now, is it leg was x and this was y, right? So did I say it backwards? So for one more unit of the leg bone, the arm bone was 1.2. That's how you interpret. Even though we didn't calculate it with 2 points to find the change in x and change in y, that is the interpretation. And finally, the y-intercept. What is the y-intercept when x is 0, y is negative 4.1135? What does that mean? Gabrielle, I'm not going to do those lines right now. You have to watch those videos, okay? Just watch those videos because I don't want to spend time doing remedial math. You watch those videos and then we'll talk next week about the whole thing. So what does this mean? When x is 0, y, that's what the intercept means. So when there's no leg bone, the arm bone is a negative. Does that make sense? Does that make sense? Can you have a negative length? So this illustrates, this is an example of extrapolation gone bad. However, it is a mathematical result. The line, if you extended the line back where x equals 0, then it would cross the y-axis at negative 4.1135. But we shouldn't do that. That's mathematically what will happen, but we shouldn't do that because that's outside the range of the values. Remember, x was between, I think the smallest one, I can't remember now. Let me see. Okay, so x was 38 till 74, right? And y was 41 to 84. So 0 for x is really far away, far enough away that this doesn't make sense. But it is the intercept to making the line, to drawing the line. You just shouldn't extend the line all the way back. So it's a positive relationship with a slope of 1.2. If I was to draw it, if I was to go back to my drawing, sorry I'm gone over, but you guys can, if you have to leave, you can go. So this is, if I went back to my drawing, then you see I don't draw, well, first of all, this is not even on the axis, right? These are both, I started the data at 34. So if I was to actually draw this, let me see if I can move that stuff. Anyway, let's just say, let me just draw it over here. I'll draw it over here. And then we're going to go. So this means that if I had a line with a slope of 1.2, no, I want to get rid of some of this. Okay, so where this is X and this is Y, notice when X is 0, that's what would happen. But in general, the data is over here, you see? I would have to extend the line to see that, but the range of the data is here. I shouldn't extend the line, but mathematically that's what would happen. So that's what we found out. Any questions? Remember, the results that I got here were because I rounded everything to 2 decimal places, so. So you're going to have different values, Hector. Yeah, if you use stat mode. So in my calculator, if I go back and see what I got in my calculator, what did I get for A and B? Let's go back. I got R of 0.9. For a B of 1 point, I could say 1.2, and an A of negative 3.66. So in my calculator, it's a little different because it doesn't round like we did. But similar, right? We got, and then using the table and rounding to do decimal places until this end, I used 4. I got an A of negative 4.113, but similar interpretation of B of negative 1.2. Actually, let me just get rid of those so it looks better. And an R was 0.995, I think I got. Okay, so very similar. Do sit and read all the notes that you need to read. You don't have to read pages 10 till 18. You can just skip those almost 10 pages and just work on the exercises that I put here. All right, so review this video, review the other ones I mentioned, and let me see, where did I mention them? Did I write them on here or the other? Oops. I wrote them on the other. Let me flash that before I go. here's your list of videos. Okay, make sure you watch all of these, review the notes, and you will be a pro at this. For next class, I'll have a question or two to ask you for review. Okay, otherwise, have a good week, and keep in touch. Bye for now. I should thank you for sticking around because a lot of people left. So thanks. Good night, everyone.